Sagittarius A is invisible, but what surrounds it is not, and what astronomers just found there resolves a 50-year mystery about how the universe's most extreme engines actually work. At the center of the Milky Way, 26,000 light-years away, a supermassive black hole sits in silence, or so it seemed. This object, called Sagittarius A, weighs 4 million times more than the Sun. It is so massive that stars orbit it at speeds exceeding 4,000 kilometers per second. Astronomers have mapped these orbits, measured them with precision, confirmed the black hole's existence beyond doubt. But Sagittarius A does more than simply sit. It pulls, it heats, it should expel. Yet for decades, when telescopes pointed toward the galactic center and searched for evidence of wind streaming from the black hole, they found nothing. The wind was missing. The absence became a puzzle. The puzzle had existed since the 1970s. Theoretical astrophysicists had argued that a black hole must produce wind. The reasoning was sound. A black hole grows by accreting material, dust, gas, stellar debris, spiraling inward from the surrounding disk. As this material accelerates and compresses near the event horizon, friction heats it to millions of degrees. At such temperatures, the material does not simply disappear into the singularity. Some of it is violently ejected, expelled outward in a torrent of hot gas and radiation. This ejection is wind. It is as inevitable as the wind from a solar flare is inevitable when the sun's magnetic field suddenly releases its tension. Yet when astronomers aimed their telescopes at Sagittarius A, they did not detect this wind. Decades passed. Technology improved. Sensitivity increased. Still, the wind eluded observation. Astronomers called it the missing wind problem. It was not that the wind was weak. Theory suggested it should be powerful enough to carve vast structures around the black hole. It was that the telescope simply could not see it. The technology did not exist. The resolution was insufficient. The darkness was too deep. Then, in June 2026, the silence ended. A team of astrophysicists at Northwestern University made the breakthrough. Mark Gorski, a research assistant professor at the Center for Interdisciplinary Exploration and Research in Astrophysics, and Elena Merchikova, an assistant professor of physics and astronomy, analyzed observations that had accumulated over 5 years. The source was the Atacama Large Millimeter Array, a network of radio telescopes positioned high in the Chilean Andes. These instruments observe the universe in millimeter and submillimeter wavelengths far too long for the human eye, but rich with information about cold dust and gas structures invisible to optical telescopes. Gorski and Merchikova combined the ALMA observations with data from NASA's Chandra X-ray Observatory. Chandra detects the hot, X-ray emitting gas that forms when the black hole expels material at near-relativistic speeds. Together, these two telescopes, one sensitive to cold gas, one to hot, created a complete picture. And the power of that picture was extraordinary. The new imaging was 100 times deeper than anything previously achieved. It was 80 times sharper. In the sharpness and depth, the invisible became visible. What emerged was a cone-shaped cavity surrounding Sagittarius A. The cavity stretched nearly 1 parsec in length, about 3.5 light-years. The opening angle of this cone measured 45 degrees, a wide funnel pointing outward from the black hole. Within this cone, the gas was cold and molecular. Beyond it, spreading outward, the gas remained. But inside the cavity, the gas was gone. Evacuated. Cleared away. The absence of gas in that specific geometry told a story. Stellar winds from nearby stars could not explain it. Radiation pressure from the black hole's accretion disk could not alone account for the pattern. Supernova explosions in the region could not create such a directed, persistent structure. Only one force could carve and maintain a cavity of this shape and size. A hot, powerful wind emanating directly from Sagittarius A, flowing outward with enough energy to push the gas aside and keep it pushed. The mechanism was clear from the morphology. The energetics confirmed it. The structure could only be explained if the black hole had been actively blowing wind for thousands of years. Calculations suggested the wind had been active for at least 20,000 years. For 200 centuries, while human civilizations rose and fell on Earth, while empires expanded and collapsed, while technology transformed from stone tools to digital networks, Sagittarius A had been breathing. It had been pushing gas outward, carving this cavity, sculpting the region around itself, and no one could see it, until now. Yet the discovery carried a surprise. Theory had predicted a violent wind, a hurricane of particles and radiation, a torrent of heat and force. The images showed something different. The wind that carved this cavity of nearly 1 parsec, the wind that had been active for 20,000 years, was described by the researchers as a gentle breeze. This paradox, a vast, powerful structure created by a gentle force, revealed something unexpected about how black holes interact with their surroundings. Mark Gorski articulated the theoretical expectation plainly. Unless a black hole exists in a perfect vacuum, it must blow a wind somehow. This was not idle speculation. It followed from the fundamental physics of black holes and their accretion. A black hole that feeds must produce wind. The wind was not optional. It was a necessary consequence of the laws of thermodynamics and electromagnetism. Yet the gentleness of this particular wind suggested that the relationship between a black hole's feeding rate, its spin, its mass, and the character of the wind it produces was more subtle than models had assumed. The implications extend across astrophysics. Every supermassive black hole probably produces wind. Every monster at the center of a galaxy is likely surrounded by a region of cleared gas, shaped and maintained by this wind. The wind is not a minor effect. It influences how the black hole feeds. It affects the material surrounding the event horizon. It shapes the environment in which new stars and planets form, or fail to form. Understanding Sagittarius A's wind is a step toward understanding all black holes, and thus a step toward understanding how the universe evolved after the Big Bang. The research appeared in the Astrophysical Journal Letters in June 2026. It answered a question that astrophysicists had posed in the 1970s. For 20,000 years, Sagittarius A carved this cavity into the surrounding gas. A wind so gentle that theoretical models had missed it entirely. A wind so persistent that it reshaped the region around the galaxy's most extreme engine. In 2026, astronomers saw what had been invisible all along.